Hello friends, this video on DNA Flock Elements Part 28 is brought to you by examfear.com. No more fear from exam. Start with the stable oxidation state of the following with the electronic configuration. The ground state as 3d3. 3d3 we know is vanadium, and for vanadium we know the stable oxidation state is +5. By the electronic configuration also we can make out that 3d5 is manganese. For manganese the +2 and +7 is the stable oxidation state. 3d8 is nickel, and for nickel +2 is the oxidation state, and 3d4 is chromium. So for chromium +3 and +6 is the stable oxidation state. Okay. Name the oxometal ions of the first series of transition metal, that is these ones, first transition metals, in which the metal exhibit oxidation state equal to its group number. See, let's see this. Scandium exhibits oxidation state of +3, and this is +3. This is 1. Titanium oxidation state of +4, and titanium is part of group 4. Vanadium oxidation state of +5, part of group 5. Chromium +6, part of group 6. Manganese +7, part of group 7. Iron +2 +3, part of group 8. Cobalt +2 +3, part of group 9. Nickel +2, part of group 10. No. Copper +2, part of group 11. No. Zinc +2, part of group 12. No. So these elements actually, they exhibit oxidation state equal to their group number. First part is clear. But now they are saying that it has to be oxometals anions. Okay, so let's see which of these has oxometal anion. Okay, let's start with manganese, the last one, Mn. So for manganese, the oxometal anions we know is KMnO4, or I can say MnO4 minus. This is anion, and this is oxometal, that is metal with oxygen and anion. So manganese is done. Manganese is one of the metal. The next was chromium. For chromium, do I have any oxometal anion? Yes. CrO4 2-. This is oxometal anion. So chromium also is an element whose oxidation state is equal to group number and has oxometal anions. The next is vanadium. Vanadium exhibit VO3- with oxidation state of +5. This is also oxometal anion. Done. The next is titanium. Titanium we have oxometal anion, and that is TiO3 2-, +4 oxidation state, group number 4, oxometal anion. Next is scandium. Scandium actually, the group number and the oxidation state matches, but scandium does not have any oxometal anions. It doesn't have any oxometal anion. So scandium will not be the part of the list. Though scandium has oxidation state equal to the group number, but scandium will not be the part of the list because there is no oxometal anion formed by scandium. Scandium typically react with chlorine, or in fact OH, but it doesn't have oxometals anions. The next question is, what is lanthanide contraction? What are the consequences of lanthanide contraction? So we know that due to poor shielding effect by 4f electrons, 4f orbitals, greater than expected decrease in the ionic radius of the elements in the lanthanide series take place from 57 to 71. From 57 actually to 71. These lanthanides, there is a great decrease in the atomic size, 204, 3, 1, 199. This decrease a lot. And with this, what happens if you compare the size of lanthanum and hafnium? If you see, there is a huge difference from 207 to 175. There is a huge difference. Okay, so element number 72, the atomic size is very less. And with this, there are consequences. The consequences are the properties of second and third transition series are almost same. These two, the properties are almost same because the size is almost same. The size, if you compare, these are almost same. Also, the high density of post-lanthanides element, because these elements now have smaller radius. Density is what? Mass by volume. Mass by volume. Since the density is radius is less, the volume is less, and but the mass is increasing. So mass is more, the volume is less. So these elements have high density. Okay. One more consequence: it decreases in the basic strength of hydroxides of the lanthanides with increase in the atomic number. Okay. Why? Because decrease in size, so the ions also, the cation size is less of the lanthanides. Okay, since the size is less, it develops what? More which character? Think ionic character. Ionic character actually decrease. Size is decreasing, the ionic character also decrease, and thus it gets more basic character as per Fajan rule. Right, between metal and OH, the ionic character will decrease because the size has decreased now. Size has decreased, ionic character decreased, and the covalent character is more and more basic. Okay, that's all we have for lanthanide contraction. There is a huge decrease in atomic size from 57, you can say, or 58 to 71, and with that the 72 element itself come up with a small size, and the trend continues. So the size is less, atomic size is less in this series, so their density is more because density is mass by volume, and they have similar properties because now if you see from here to here there is increase in size 160 to 175, from here to here there is no increase in size. As you go down the group, typically the size increase, but here it is not following the trend. Right, for example, more examples you can see. Here to here size increase, but here to here size is less actually. Here to here size increase, here to here size is less. Here to here size increase, but here to here size less. Here to here size increase, but here to here size less. Here to here size increase, here to here size less. This is all because of lanthanide contraction. What are the characteristics of transition elements and why are they called transition elements? Which of the D blocks elements are not regarded as transition elements? See, transition elements we have told are the elements which have partially filled d orbital in their stable or ionic form, right? Stable oxidation or stable oxidation state or my elemental form. And these are transition metal because they are transitioning between the metals and non-metals, S and P block elements. And we have already told zinc, cadmium and mercury, these three metals are D block elements, but they are not called transition metals because in their elemental state and also in their oxidized state, their d orbital is filled. The question is, in what way the electronic configuration of transition metal is different from the non-transition metal? Very simple, it's all about the d orbital. So if the d orbital is filled, it is non-transition metal. For example, zinc, the electronic configuration is argon 3d10 4s2. This is my non-transition metal. Talk about transition metal, you can take, there are some examples. Chromium example, if you take 3d5 4s1. If you see, D can accommodate 10 electrons, it has only 5 electrons. Iron 3d6 4s2. D can accommodate 10 electrons, iron has only 6 electrons. So these are all transition metals. Okay. Explain the reasons. Transition metals, many of its compounds show paramagnetic nature. See, I told you paramagnetic nature is because of unpaired electron, right? And d orbital can accommodate 10 electrons, and most of the transition metals, they have unpaired electrons. Since they have unpaired electrons, they show paramagnetic nature. Explain the reason why the enthalpy of atomization of transition metal is high. Enthalpy of atomization of transition metal is high, as I told, is because of strong metallic bond. Because of here also unpaired electron. This unpaired electron creates strong metallic bond, and this metallic bond is strong, so you need high energy to actually convert from solid to gas. And this is my enthalpy of atomization. Why this transition metals are colored compounds? The transition metals are colored because of, again, unpaired electron. This is also unpaired electron. Because of unpaired electron and DD transition, they are colored. Please note, for example, zinc is not colored. Why? Because zinc, the electronic configuration is 3d10 4s2. If you talk about this zinc, this is how it is: 1 2 3 4 5 6 7 8 9 10. All this, the d orbital is completely filled. There is no scope for movement of electrons. Zinc is not colored. Okay. Transition metals and their many compound act as good catalysts. Again, the reason for the good catalyst, as I told you, was the variable oxidation state. And they form unstable complex. This unstable complex is also because of, again, unpaired electrons and vacant d orbital. And they also provide surface area for reaction. Again, this is also because of unfilled d orbital. So most of these property of transition metal is actually because of unpaired d electron or unfilled d orbital. What are interstitial compounds? Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.